we said it's much more about research based, is geopolymer. So like my colleague introduced earlier, geopolymer is also a kind of cement, or you can produce concrete, so whatever you can do with the Portland cement or the magnesium cement, you can do similar thing with the geopolymer. So these samples were actually produced here on this campus. So the picture that you see is also 20% wood with geopolymer. And with geopolymer, when we talk about geopolymer, we are talking about a cement. Just the geopolymer is a cement from any material containing aluminium and silicon. These are the two main components that need to react for us to form a geopolymer. And you saw that we have these two aluminium also, the aluminium and silicon also in cement. So it's a similar technology, but here, the difference is here we are utilizing residue or waste. So, you know, we burn a lot of coal to produce energy for our homes and for our use. So after burning the coal, there is a bit of ash. We burn a lot of garbage to produce ash and other things. So once you have this ash, we don't just deposit them in landfill. We try to find a use for this material. And so geopolymer is just simply by alkaline activation, so adding alkaline medium or alkaline solution to this material, then you get a solid. So we don't activate it with water. In cement, we add only water, but here we put what? Alkaline activator, and the alkaline activator is mostly sodium hydroxide. So we form sodium hydroxide solution with or without silicate. Without its silicate, then you just add it to this residue, then you form these hardened products. And in Austria, they've built a whole airport from, I think, the runway, I don't remember, and a bridge. And I think that even some part of the airport building was also from this geopolymer. But now more research is still ongoing to at least, if not eliminate cement, at least act as a subsidy for cement, because we are producing a lot of carbon dioxide from the cement production. So we try to find other subsidies and other things to help in this process, so to utilize this residue by just alkaline. So we have the source of material that we produce, and this is just a simple scheme illustrating what is happening. Like cement, we saw what was happening in the process, but here it's a simple process, but a bit complicated in reality. So we have a source of aluminum silicate, meaning any material containing aluminum and silicon as our raw materials, so fly ash. From the mineral industry, we have the slag, we have the metakaolin, we have the hacks from rice. Then we produce these. We add the alkaline medium, we add the sodium silicate. Then the first process that it goes through is dissolution. So like we saw before, where they produce the amorphous gel, here also with the dissolution, we have something like a gel. Once the activator gets in touch with the particle surface, they begin to dissolve into more liquid material. Then in the dissolution, we are utilizing water. Then after the dissolution of the aluminium and silicate source, it goes into the rearrangement of the species. Then with the rearrangement of the species, they are still in the liquid form, so the reaction is still ongoing. Then with the rearrangement, from there, we have water coming out to the rest of the process. The difference between this and the cement reaction is with cement, we are consuming water. So more water, it gets more solid and hardened. But with this material, in the beginning, we are using water in the dissolution and the hydrolysis and the species equilibrium. So in the dissolution, we are using water. But after the dissolution process and the hydrolysis process, we are now eliminating water from the system because we don't need water in the product. The water needs to come out so that the product can bind. Then it goes through the gelation, still in the gel form, and the reorganization is still ongoing. The atoms are rearranging in a specific way. Then till the hardening, the polymerization process. There is also water coming out, but you cannot eliminate all the water from the process. Always there is still a bit of water in there. in the final product. Even for the pure hardened geopolymer, there is still a bit of water, but not so much. And with the geopolymer wood bonded composites, what we have is we have also the wood, like before, wood or fiber source, and the raw material. Then we try to activate the raw material with this alkaline medium. Some people first produce the celery, so they produce the geopolymer paste first, then they add the source of fiber or wood. Others also try to mix the wood with the fly ash or the metakaolin or the slag. Then they add the solution, the alkaline solution, to form the solid product. They all have their own disadvantages and advantages. But in research, I realized that it doesn't make much more difference, whichever you produce. So this product is 20% wood and the rest is the pure geopolymer. And this is a research conducted here by myself and with other help from colleagues. And here we have a material. Actually, this material, this is the property of this material. That is what we are showing here. And it's made up of 20%, like we know before. Then they try to find the density, what is happening. Like I said, in the cement, the strength you see begins to develop, so the density, they begin to change also with time. So here we have the density, and we have, in the mixture, we have wood, and we start with wood that is totally dry. So wood with moisture around 1.3%. And we have wood that is around the equilibrium moisture content around 12%. Then we have wood that is around fiber saturation point, and wood that is above, so 60%, and we have that is almost 90% wood, water. So every component is the same, but just the wood that is added have different moisture content. So when you put in, what is happening here is for 7 days and 21 days. For 7 days, you realize that the density is almost the same. There's no sharp difference between them, even though it begins to reduce when you have much more weight. But what happens is after 21 days, we realize that there is water coming out still from the system, because from the previous slide, we realized we don't need the water in there. The water has to come out, whether from the wood or from the geopolymer. So what happens is here, for 7 days, they look the same, but for 21 days, they begin to reduce with time. It's only between the wood with 1.3 and 12% that you realize there is increase in density, because here there is less of water in the beginning. So with the polymerization, they are still forming new products. So with hardening, the density increases. But with these three, the one around fiber saturation point and above, what happens is there is more release of water than the formation of new products. So once there is more release of water, definitely the mass goes down and the density goes down with time. But here in the beginning, there is much less release of water, so the density is higher after 21 days. And then this is just showing their strength. And with the strength, when we have wood that is much more drier in the beginning, in the mix, the strength is far better than when we have it when it's totally wet. Because when you are totally wet with time, the water is coming out. This is the specific strength, so the strength divided by the density. So the issue of density has been cancelled out. But what happens is, once the water comes out, definitely you are creating pores, because the water has to get out through some pores, so they create their own channels and other things, and you are reducing the strength of the material because there is less pores. Now there is also a bit of less compactability between the surface of the wood and also the material. So the density, the strength, the specific strength also reduces with increasing moisture. And this is also a work from one of the previous students of Andras Kauser. And this research also contains, so here what we have is, we have 20% of the wood material in there, but here we have the compression strength, and here we have the pure material without wood, so the strength is somewhere 76 megapascal. And when we replace it with 20% of wood floor, so very fine wood, when we have it, the strength is somewhere around 38. So cut to about half with 20%. Then when we put in wood fiber, the strength goes down. Then when we put in wood particles, the strength goes down. Just like, that is why I said from the video, the production of this mineral bonded composite depends on your application, what you're using it for, what is your strength target, how are you going to use this material, what do you need, the density and those things. Because here we have different wood. We have wood that is like a powder, but it's better, there is better compatibility, so the strength is better. Here we have wood that is a fiber, and mixing fibers, like I told you, mostly mixing fibers is not easy, especially on the laboratory scale. If you mix fibers, sometimes they form these balls and other things. The dispersion of these fibers is not so easy with a laboratory mixer as compared to the industrial scale. They have better mixers, but in the laboratory we have a different kind of mixer. So the mixing is also a problem. And with particles also, depending on the source of wood and other things, like my colleague said earlier, there are other sugars and other things, but it has not been confirmed yet whether all the sugars affect geopolymer or not. But in cement, much is known about this influence. But with geopolymer, still research is ongoing to find out whether the extractives of the wood are affecting it or not. So research is still ongoing. And this is what happens to the density also. You realize that when you have the pure one, the density is much more higher. So that is also can be a factor why we have a higher compression strength for that. And the density is reducing. This is 20% wood flour, but the density is higher than when you put in 20% of wood particles. So this is what is also happening in the mixture when you have a geopolymer. And from the boards that I showed you, we have two specific ones from geopolymer. Can you? I only need the last one first, and this one, the one closer to Anne. Yeah. So, thank you. So this were produced also here using our laboratory technology. So we have this geopolymer from metakaolin, and it's also a board also with 50% spruce, and this is also from fly ash from coal, and it's also 15% spruce. But the density is totally different because of the starting material. And also the color, you can see this, we didn't apply any color. Mostly metakaolin is a bit whitish in the beginning, but with time the water was coming out and we didn't store them under the right conditions, so the color, you see, begins to change on the edges and other things. But these were produced here, and fly ash is mostly grey, so this is the original color of the product, so we didn't apply any color or something. And metakaolin is much more lighter, but occupies much more volume, especially, and needs much more water and in solution during the mixing, but this one needs less. So they have their own advantages and disadvantages, but these materials are possible, and also you can use them in place of these cement bonded materials, because they are also mineral bonded materials and they have similar properties and strength as compared to strength. So I think, thank you.